Hi friends, so in this session we are going to see the equivalent spring stiffness. Now why the equivalent spring stiffness is required? So we'll consider one example. Suppose in any single degree of freedom vibrational problem, suppose two springs are given which are attached to one mass having same or different spring stiffness. Then in this case, to determine the natural frequency, the circular frequency we can determine by using the formula root k by m. So here to determine the omega n, that is the circular frequency, or the natural frequency, 1 divided by 2 pi root k by m. So in both the formulas you can see here we will require only one k value, that is the stiffness. But in the problem they have provided the two springs which are attached to the mass. So in that case we will have to convert this given system into one spring system, that is this one. When we convert this system, then we can put the value of this k into this formula, and when we convert the parallel combinations or series combinations of the springs into one spring, that spring is called equivalent spring. Means the result of this system and the earlier system is same, so it is going to provide the same result. So this combination is called the equivalent spring. So in the figure which is shown, these two springs are in parallel. Now how to determine the parallel combination and series combination? Here I will draw one more combination. Suppose this is the first spring, then this is the second spring, and the mass is attached. So there will be number of springs which are attached to one mass. Now I will consider the stiffness of both the springs is same. Now this combination, if you see here, the total displacement of this mass is x. Then there will be a small deflection of first spring, then there will be the small deflection of second spring, and the total deflection will be x. So here we can write x is equal to deflection of spring 1 plus deflection of spring 2. Means in series combination, the total deflection will be addition of deflection of each spring. But in parallel combination, here you can see the deflection of both the springs is same. Means here the total deflection of this mass will be equal to deflection of first spring and equal to deflection of second spring. So this is most important thing which is required to determine the combination of springs is series or parallel. So keep in mind that for parallel combination the deflection of each spring is same. Now to understand this concept, we will consider one more example, and you have to give the answer for this combination. Just think and give the answer. Suppose this is the spring stiffness K1, K2, this is the mass. You have to tell what is this combination, it is series or parallel. Now I will give the answer. See, this mass is going to displace. Suppose this displacement is x. Then the spring 1 will elongate in downward direction, and because of that the spring 2 will be compressed. Both the ends of these springs are closed. So whatever the elongation is in the spring 1, the same compression will be in spring 2. Means the deflection of spring 1 and spring 2 is same. So this combination is parallel combination. Okay. So with the help of this deflection, that is x is equal to x1 plus x is equal to x1 is equal to x2, then that combination is parallel combination. Means in parallel combinations, deflection of each spring is same. Okay. Now we'll determine the formula for series and parallel combination. Okay, so this is the derivation of series and parallel combination. So first here I'll consider the series combination, and simultaneously on the right side I'll do for parallel combination. Okay, now in the series combination, for this study purpose I am going to consider only two springs. So consider one spring mass system with two springs attached to one mass. Sorry, I have taken a parallel combination. I will convert into the series combination. In the series combination, I will have to consider two springs in series. Okay. Now this is the series combination. Consider the stiffness of spring 1 is K1, stiffness of spring 2 is K2, and it is subjected to displacement of x. Now as we have seen earlier, that from this combination the total deflection x will be equal to deflection of spring 1, this one, plus deflection of spring 2. So x is equal to x1 plus x2. Okay, and most important thing, the force which is acting. The force acting this throughout the spring will be same. So suppose if I apply the force F on this system for the displacement x, then the force acting throughout this system is same. So here the force F will be equal to force in spring 1 equal to force in spring 2. Okay, so this is for the series combination, and this one is very much important, that the addition of the two deflection will be equal to total deflection. Similarly, I can write for parallel combination. In parallel combination, I will have to take the two springs in parallel. You can take n number of springs, but for the study purpose I have taken only two springs. Consider stiffness of first spring is K1 and second spring is K2. Means this mass is attached to two springs. Okay. Now suppose the displacement of this mass is x, and I applied the force F for this displacement. Then in parallel combination, as we have seen, the total deflection x will be equal to deflection of spring 1 plus deflection of spring 2. Now the most important thing is, when we apply the force on this system, then the force will get divided, because the force will get divided. Here I have made one mistake, that I am going to modify it. The x1 will be equal to x2, because in parallel combination the displacements are equal. Now the force here acting will be divided into two parts. Means some of the part of this F will be taken by spring 1 and the remaining part will be taken by spring 2. So the force will get divided into two parts. So it will be F1 plus F2. So if you compare with the series combination, in series combination throughout all the springs the force remains same. In parallel combination the force get divided. In series combination the addition of displacement is equal to total displacement. In parallel combination all the displacements are same. So To determine the series and parallel combination, you will have to keep in mind this one. That is, for all the springs, the displacement will remain same. Now, I am going to make the derivation. Now, I will write one formula here. The spring force we write as F is equal to K into X, stiffness into displacement. Okay, so F is equal to Kx. So I'll write this F is equal to Ks here. So from this one, X will be equal to F divided by K. It will be equal to F divided by K. So replace here. So X will be F divided by K. X1 will be F1 divided by K1. X2 will be F2 divided by K2. Okay. Now, as we have seen in series combination, all the forces are same. So F equal to F1 equal to F2. So from this I can write F by K equal to, I'll take this F constant because F1 is equal to F2. So when I take F common, that is F1 and F2, so this will be equal, this will be 1 divided by K1 plus 1 divided by K2. Okay, here we have plus sign. Now the F that we have taken common will be cancelled from this equation. So F is cancelled with F. So 1 by K is equal to 1 by K1 plus 1 by K2. So this is the formula for equivalent spring. Means if I replace the given spring, means this spring if I replace, then I can draw this spring like this one. Mass will remain same, displacement will remain same, but the two springs will convert into one spring and we call it as KE, that is equivalent spring. And the formula for the equivalent spring is this 1 by K. This K is nothing but the equivalent spring stiffness. Okay, so 1 by K is equal to 1 by K1 plus 1 by K2. Now suppose there are 5 springs. So we can write 1 by K1 plus 1 by K2 plus 1 by K3 plus 1 by K4 plus 1 by K5. So you can write for n number of springs. So this formula will provide you the equivalent spring stiffness for series combination. Now similarly I'll do for the parallel combination. Okay. Now for parallel combination we know that displacement of each spring is same. So in the star mark you can see X is equal to X1 is equal to X2 and the force will get divided. So F is equal to F1 plus F2. F means total force, F1 means force acting in spring 1, F2 means force acting in spring 2. Now from this formula F is equal to Kx, that is the spring formula, we will have to write here F is equal to K into X is equal to F1 K1 X1 plus F2 K2 X2 K2 X2. Now but we know that here we know that X is equal to X1 is equal to X2. So I take X common because X1 and X2 is equal to X. So in bracket the K1 plus K2 will be remained. Okay. Now we can cancel X. So the formula will be K equal to K1 plus K2. Okay. Now this K is nothing but the equivalent spring stiffness. So here I will write KE. Now we can replace this given system into a single spring. So this is the single spring and this one is the mass. Okay, and this single spring stiffness is KE. Okay, so we have reduced the parallel combination into one spring. and this one spring, why we require that we have seen earlier. So this concept, that is the equivalent spring concept, will require to determine the frequency of the system. So we'll have to convert into a single spring. Okay, and these are the two formulas. Now in parallel combination, suppose there are n number of springs which are parallel, then we can directly write K equivalent is equal to, that is stiffness equivalent, equal to K1 plus K2 plus K2 n number of times. Okay, we will get the answer. Thank you.